All good. It is my pleasure to introduce Olivier Talagrand. Olivier is an honorary research director at the Centre National de la Recherche Scientifique, and he works at the Laboratoire de Météorologie Dynamique in Paris. So when we were coming up with the speakers for this session, we obviously wanted the godfathers of data assimilation, and it is impossible to think about data assimilation without thinking about Olivier Talagrand. In 1987, himself and Philippe Courtier wrote a seminal paper in our field, the variational assimilation of meteorological observations with the adjoint vorticity equation, a two-part paper, one part with theory and the other with numerical results. And this was the seed that developed into the so-called adjoint technique and the application of it into numerical weather forecasting, but was eventually denominated as 4D bar. Obviously, the fourth dimension being the time dimension. Took 10 years until in November 1997, ECMWF implemented 4D bar operationally and improved their skill considerably. Just a couple of years ago, we had a really nice event on 20 years of 4D bar in ECMWF. So Olivier Talagrand, he has influenced our field enormously, not only with 4D bar, but considering other contributions that he has had to nonlinear aspects of data simulation. He has also worked on observation sensitivity. He has done work on predictability, ran histograms, the so-called Talagrand diagrams, and in general applied concepts from control and optimization theory in numerical weather prediction. He has won a multitude of awards. Perhaps the one I want to mention is the Louis Fry Richardson Medal, the medal from the European Physical Union in the division of nonlinear processes in geoscience. In 2004, Olivier was the recipient of this prestigious award, an award that was also given to Michael Guild some years before. So we have very big luminaries receiving this award. Personally, I have had the pleasure to work with Olivier organizing EGU sessions on data simulation, model error. And I think one of my favorite personal stories comes from Mohamed Yartak, who worked with him in École Normale Supérieure in Paris for a while. And he told me that if you go to Olivier's office, you have to have very good navigation skills. Apparently his office is full of piles of papers higher than a meter because he never throws away anything, and his production has been huge, so I can imagine the height of those piles. So with this, I give the floor to Olivier. Olivier, please tell us about a brief history of data simulation.
Okay, thanks, Javier. Thank you for the invitation, and good afternoon to everyone. So I'm going to present a brief history of data assimilation, which actually started from a rather minor task, namely the definition of initial conditions to numerical weather prediction. Numerical weather prediction started for good in the late 40s at the Institute for Advanced Study in Princeton, New Jersey, under the leadership of John Weilman, in a group comprising, among other people, like Jules Charney, Norm Phillips, Fjordhoff, and Jos Magarinsky. So just was not, at the beginning, defining the initial conditions of the numerical weather forecast was just considered as a very minor task, the real thing being, of course, the forecast itself. But difficulties gradually arose. First, it was necessary to need initial condition with appropriate spatial scales, and that led to the introduction of structure functions, which are now incorporated in what is called the background error covariance matrix. Need for defining initial condition in approximate geostrophic balance, that led to what was called at that time initialization. Need realization that useful information was present in observations, particularly satellite observations that were distributed over time, and so that led to the need to introduce the dynamical model to be used for the prediction in the process of definition, in the definition of initial conditions. And it is in that context that the word assimilation was coined in the late 60s. Satellite observations, in addition to being distributed continuously in time, are indirect in that when done very directly on the physical parameters, typically pressure and temperature, which we want to introduce in our numerical model. And of course, there were a very significant increase of the number of observations, so a need for powerful and robust algorithms. And finally, it was realized that weather prediction was very sensitive to initial conditions, which even it in a sense doomed long-term weather prediction, stressed particularly the importance of defining as accurate as possible initial conditions. That's the number of data used every day at the European Center for Medium Range Weather Forecasts, ECMWF, located in England. Actually, this graph goes to 2014. There was a huge increase of the number of observations in the years in the early 2000s. Since then, the number of observations that are used have not significantly increased, and around 10 million of individual scalar observations are used at ECMWF over every 6-hour period. That gives an idea of the number of pieces of information to be processed. At the same time, the proportion of resources devoted to assimilation in numerical weather prediction steadily increased over time. Now, at ECMWF, about 40% of resources devoted to the whole operational chain, including the ensemble forecast, is now devoted to 24 hours of assimilation. Originally, before computers were available, meteorologists worked on charts drawn by hand with a pencil and an eraser. And what typically meteorologists did was to draw a chart for a forecast for the following day or for the days to follow. And when he came back to his office on the following day, he plotted on the chart the new observations that had been acquired in the meantime. And he did what was called the analysis of the situation. And it was known that some meteorologists were more expert at that exercise than others. And when computers became available, of course, they were used to perform the same task that was performed before by hand. And that led to numerical algorithms, and people spoke of objective analysis by opposition to the subjective analysis that were performed by human individuals. And the principle was the same as when the analysis was done by hand, that is, apply correction to a first estimate by extrapolating differences between that first estimate, first guess, and the observations. And methods were early developed for that. And one particular method gave wide acceptance, what has become known as optimal interpolation, which was known in meteorology largely through a book by the Russian scientist Lev Gandin. And the principle is very simple. We have an observation, yj, at a number of points in space. We want to estimate an unknown quantity x, some meteorological variable at some breakpoint of the model. And we look for X under the form XA, where A stands for analysis. The word analysis has survived for a time of pre-computer, and the coefficient of XA in the form of an affine function of the YJs, the alpha and beta J's, being determined as to minimize the expected quadratic estimation error between XA and the real value. And this, of course, requires a priori explicit knowledge of some statistical properties of the field under consideration. And it is sufficient, because it is a quadratic problem, to know the first order moments, which define a background to be, or first guess to be corrected, and the second statistical moments, which define the correction to be made on the first guess. And in that approach, each observation comes with its own influence function, also called representative, which is simply its statistical covariance with a variable to be estimated. And the correction performed on the background is a linear combination of all representatives, which each one with its own weight. And that's an old picture of a representative associated with a measure of surface pressure in a particular station, which is Stockholm, and an observation performed at this point influences the analysis through a term added to the background, which with spatial variation as shown by this graph. And these are covariances obtained under the hypothesis that the geopotential and width increment are in geostrophic balance, which shows starting from an isotropic pattern of covariance for the geopotential. On the top left, you have, for instance, at the point in the next panel to the right, the covariances between the measurement of geopotential in the middle of the panel and the U component of the wind in other points, and so on, for all combination of variables. And this is a very old picture from Andrew Lawrence. He's in the audience today. On the left, we have first guess of sea surface pressure and wind at 10-meter wind. A number of observations have been put on it. For instance, there is an observation at this point here, which shows that the pressure is lower than in the first guess. So the optimal interpolation corrects the corresponding field, and it deepens the small depression at this point. And this is essentially how optimal interpolation works. When one uses the word optimal interpolation, it means that the background covariances which defined the representatives is taken independent of the state of the flow, taken once for all, climatological or seasonal, but independently of the particular situation of the flow. And at a later stage, optimal interpolation was performed through iterative minimizing process, and in that context, optimal interpolation has been called 3D VAR, but is essentially another algorithm for solving the same problem. And optimal interpolation has been abundantly used and is still used in many applications, and was the standard method of assimilation of meteorological observations for a number of years. One particular problem was that when used a primitive equation model, which doesn't impose a strict geostrophic condition for geostrophic balance, the numerical integration showed irrealistic variation of the surface pressure associated with irrealistic vertical velocities and irrealistic rainfall, which spoiled the forecast. you have here a full curve, an example of such an imbalanced integration. And it was necessary to smooth out these unrealistic oscillation. And that particular process of smoothing was called initialization. The word does not exist anymore. It's because I'm speaking of a history of data assimilation that I mentioned today. Initialization at that time was smoothing out unrealistic oscillation. These oscillations were not numerical artifacts. They were gravity waves, which can exist in the atmosphere, but which were present in the model in an unrealistic amount. And it's still there. I mean, I've just inquired, especially for this presentation today, and at ECMWF, very still in the objective function that is minimized in a 4D var, very still a term which is intended at smoothing out unrealistic values of divergence and surface and variation of surface pressure. So, in optimal interpolation, OI, the particular situation of the field was not taken into consideration in defining the variances convergence of the error on the background. And this shows, which was produced, result obtained by my colleague François Boutier, starting on the top panel from an isotropic positive correlation between the geopotential at a given point and geopotential at other points, plus for a complete field. This was evolved, François Boutier evolved this initial uncertainty by repeated integration of a simple shallow vector equation models. And after 6 hours, he obtained the panel in the middle, and 24 hours, the panel in the bottom. You see that the spatial extension of the covariances has increased very significantly, that the pattern has been elongated in one particular situation, north, west to southeast in the particular situation, and that on either side of the original positive kernels, 2 negative kernels have appeared. And this kind of evolution is entirely due, it depends on the particular situation of the flow, and in particular, of the particular instabilities in the flow that may be present on that day. And so it was, in fact, the need for determining the temporal evolution on the uncertainty on the state of a system is the major difficulty in assimilation of meteorological and oceanographic observation. Evolving the state itself is done by the model, which is available in the first place. But evolving the associated uncertainty, which of course requires computing power, is in fact the major difficulty in assimilation. And 2 classes of algorithms have been proposed and are still largely used for that purpose. Kalman filter on the one hand, especially in its ensemble form, and variational assimilation. But before I describe those things in a little more, in more detail, I make a few comments about the very purpose of assimilation. The very purpose of assimilation is to reconstruct as accurately as possible the state of the atmospheric or the oceanic flow in a system, using all available appropriate information. And that information essentially consists of the observations proper, which vary in nature, in resolution, in accuracy, and are distributed more or less regularly in space and time. And the physical laws, which govern the evolution of the flow, and which are available in practice in the form of a discretized and necessarily approximate dynamical model. Asymptotic properties of a flow, although they are necessary consequences of the physical laws, can usefully be introduced, as I said, in the process of assimilation, as I said a few minutes ago about initialization. Both observations and model are affected with some uncertainty. So there is an uncertainty in the estimate that it is important to quantify as accurately as possible. And this leads to consider assimilation as a problem in Bayesian estimation. That is, determine the conditional probability distribution for a set of a system, knowing everything you know. Of course, that requires to describe all pieces of information introduced into the assimilation in the format of a probability distribution, which may not be easy. Assimilation is actually one of many inverse problems, and in most of these problems, it is the Bayesian approach which is followed. And the basic equation for the estimation, even if the physical or real-life context is totally different, are the same. Now, there are difficulties that are specific to assimilation of meteorological observations. First, the very large numerical dimensions of problems to be solved. There is something like, I didn't mention the number, but I mention it now. There is something between 10 to the 6th and 10 to the 9th parameters to be estimated. And there are several tens of millions of observations per 24-hour period. And of course, the difficulty is aggravated in numerical birth predictions by the need for the forecast to be ready in time. There is no right to a second try in case something goes wrong. It must work every day. Totally reliable. And in addition, the underlying dynamics is non-trivial and can actually correct it. Well, I said that if errors are additive and Gaussian, optimal interpolation achieves Bayesian estimation. Bayesian estimation is easy to state. It is impossible to implement in practice because it is impossible to explicitly describe a probability distribution in a space with dimension even as low as 10 to a third, not to speak of a dimension of present numerical normals, as an aspect of the so-called curse of dimensionality. And the probability distribution of errors in the data is itself very, very poorly known. Little is known about the statistics of the errors in the model. By the time you accumulate enough statistics to have some knowledge, some statistical knowledge of the errors in the models are constantly modified and the model will become obsolete. So, no, impossible. But still, the Bayesian approach is very useful in that it tells us the way to go. It tells us what the meaning of the myriad of coefficients which one can introduce in assimilation. It gives meaning of what we do. It tells us the way to go. It helps us making the link between what we introduce in the method and what we obtain from it. And in that sense, the Bayesian logic is very important, very powerful. In practice, from the numerical aspect, we have to restrict ourselves not to the purpose of defining a whole probability distribution for the state of the atmosphere or the ocean or whatever we want to study. Two modest approaches have been developed. One is to obtain some central estimate of the conditional probability distribution, an expectation, a mode, plus some estimate of a corresponding spread, standard deviation. This is, in a sense, what variational assimilation has been doing so far. And the second is to produce a number of estimates that are points in state space that are meant to sample that conditional probability distribution. That is what ensemble kernel filter does. And in practice, ensemble of sizes between a few tens and a few hundreds tend to be sufficient. At least one can obtain very good, very useful results with ensembles of those relatively small dimensions. So, a brief description of the Kalman filter. We have observations that are distributed in time. Yk equal xk. Yk is the observation vector of observation. Xk is the unknown, the real state of atmosphere described in the format in which we want to describe it. Yk equal hk xk, where hk is the so-called observation operator, assumed here to be linear, plus an error epsilon k, which has covariance matrix Rk, and which is uncorrelated in time. And we have an evolution equation, the state of time k plus 1, xk plus 1, equal mkxk plus eta k, where mk is, for the time being, linear model operator, which we know, and we are capable to compute, given an xk, we are capable to compute mkxk, but that is not the real evolution. The revolution is mkxk, starting from xk, is mkxk plus an error eta k, the model error. The model error is that part of the reality which is not described in the model. And eta k is assumed to have covariance qk and to be uncorrelated in time. And all that is supposed to be uncorrelated in time. And this gives the classical equations of the Kalman filter. At the time k, we have a background, xbk, xb, b for background, or b for before, and an associated error covariance matrix, pbk, which defines the uncertainty on the background. And there is an analysis step, xak, a for analyzed, or for after, equal xbk, plus a correction that is proportional to the innovation, that is the difference between the observation vector and what the background predicts for the observation vector, times a matrix which is called the gain matrix. Actually, that formula is the formula of optimal interpolation. And then it is possible, at least in principle, to determine the covariance matrix of the error in the analysis, PAK equal PBK, minus a term which is positive and which represents the gain brought on the knowledge of X by the knowledge of the observations. And then once this analysis has been made, one makes a forecast step to the next observation time k plus 1, x background at time k plus 1 equal x analysis at time k times multiplied by the model, and the associated uncertainty, the associated variance covariances, evolve according to the equation PBK plus U equal two terms. The first term on the right represents the evolution of the uncertainty through the dynamics of the model. The second term represents the evolution of the uncertainty through the errors in the model. And this is called Kalman filter, which stimulated interest, early stimulated interest in meteorology in particular, was very much studied by Michael Gill, who will talk after me. And of course, this has to be started from initial estimate at time 0. And in case observation and model errors, epsilon and eta are globally Gaussian, Kalman filter produce at any time k the conditional probability distribution for xk, conditioned by all data up to that time, and that condition probability distribution is itself Gaussian. Well, the equation PB equal k plus 1 equal blah, 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 describe the temporal evolution between two observed instants of uncertainty at the state of the flow. I said that is precisely the main difficulty in assimilation. It is much too costly, assuming we know everything in the right-hand side. It is much too costly to be implemented in a real situation. So two solutions have been proposed. Low-rank filters in which the covariance matrix, full covariance matrix, is reduced to a low-rank matrix restricted to modes in state space in which it is known, or it is assumed, but a large part of the assimilated uncertainty is concentrated. And the ensemble Kalman filter, introduced by Evensen, in which the uncertainty is described by an ensemble of points in state space. And in that case, the ensemble of points, q tends to a few hundred, are evolved in time through the full model, which eliminates any need for linear hypothesis as to the temporal evolution. This eliminates any need for a linear hypothesis in the dynamics. Okay, the ensembles are updated, and I just mentioned that there are difficulties. The the covariance matrix PV has a tendency to collapse for several reasons, and this needs to be corrected by covariance inflation, basically determined on more or less empirical heuristic procedure, and also because of a relatively small size of the ensemble, spurious correlation can appear at large geographical system distances, and this requires the need for localization of the covariance matrix in physical space. And this figure, which is also rather old, compares the performance of an ensemble Kalman filter considered by Mang and Zhang, the performance of an ensemble Kalman filter, which take into account the evolution of uncertainty of the state of the flow, and a 3D VAR, which doesn't take into account the evolution. The curve to be considered as the full curve, they represent errors in the background, the comparison, the innovation. The red curves correspond to the error obtained with ensemble Kalman filter, and the blue curves get obtained with 3D VAR. And you see that systematically, the error in the ensemble Kalman filter is smaller than the error in the 3D VAR. This is because ensemble Kalman filter takes explicitly into account the evolution of the uncertainty and the state of the flow, which 3D VAR does not. Size of ensemble, well, it's a few tens, few hundred. This is related to the number of unstable modes in the system. Well, ensemble Kalman filter exists in many variants. There is a real zoo of variants of the ensemble Kalman filter, and it is used for many applications, both in operation and in research. Variational assimilation. Well, the same data as I described for Kalman filter. A background, 0, observation distributed in time, a model, which is not exact at this stage, not supposed to bear an error. Again, covariance matrix QT. We take a sequence of model states over the observation period, and we want to obtain a sequence which fits as closely as possible the reality. And under hypothesis errors, it is seen that the best sequence of states is the state sequence which measure this scalar function, which is the sum of the misfit between the sequence of model states and the initial conditions in the initial background, weighted by inverse of the corresponding error covariance matrix, plus a summation of terms which measure the misfit between the observations and the analogs of the observation in the sequence of state, weighted by the inverse of the corresponding covariance error covariance matrix, plus sum of the time of the misfit between the sequence of states and the model equations, weighted by the inverse covariance matrix. And the principle of variational assimilation is to find the sequence which minimizes all that. And in linear case, this solves the same problem as Kalman filter, in the sense that the states produced by both algorithms and the end of the assimilation window are the same. In addition, if the errors are Gaussian, the algorithm, like Kalman filter, is Bayesian. Well, variational assimilation provides information both forward and backward in time. It is a smoother sense. It is different from the standard Kalman filter. It can include nonlinear operators. One can minimize this function with nonlinear operators. Well, all right. It does. It can also include temporal correlations between observation, between data, which standard Kalman filter doesn't do. But contrary to Kalman filter, it does not produce an explicit estimate of the uncertainty of the final estimate. And contrary to the Kalman filter, there is no obvious cycling of estimation error for one assimilation window to the next. Kalman filter runs smoothly in time. Variational assimilation requires to be restarted at some time zero. In practice, variational assimilation has been implemented first and is still largely implemented under the hypothesis that the model is exact. So it is strong constraint variational assimilation by opposition to weak constraint variational assimilation, which takes model error into account. So strong constraint variational assimilation amounts to minimizing the scalar function of the initial state at the beginning of the assimilation window, which is the sum of a term, the term deviation for the background, a deviation misfits with the observation. And as I said, at TCMWF, they have now at least a third term, which is measure the amplitude of fluctuation of the divergence field. And maybe there are others, but these two terms are the most important. And of course, psi k plus 1 depends on psi 0, psi k 0, psi 0 through the model equation. Now, the problem there is to perform explicitly the minimization. And in the large systems which were considered, each step of the minimization is what was done through an iterative, minimization algorithm, each step of which requires the explicit knowledge of the local gradient of the objective function. And the computations were made possible from the use of the adjoint model of a dynamical model. The adjoint model is obtained by linearizing the model if it is nonlinear, and then taking the adjoint in the sense of the theory of adjoint operators of the linearized model. And each gradient for a given psi 0, the local gradient of the objective function, is obtained by integrating the direct model over the assimilation period and integrating backward the adjoint model over the assimilation period to the beginning. And to see the impact, these are results which are obtained by Jean-Noël Thibault at ICMWF. You see here the impact of the observation of the U field at a position somewhere in between channel between France and England, and you see the impact of this particular observations on the geopotential field at the level of observation and at higher level, which is not very visible. And this impact is the representer introduced by the metric PB introduced at the beginning of the assimilation period. And that's the same thing. 24 hours of variational assimilation. Only one observation, but the background at time 0, 24 hours before. And not the impact of that observation. Totally different. And of course, the impact is much larger. It goes much higher in altitude. It extends much farther in the horizontal direction. At 200 hectopascals, the impact of this observation extends 2/3 into the Pacific Ocean. So totally different impact, which depends on the particular evolution of the flow over 24 hours of assimilation. That was taken for a situation in which there was a strong storm over the channel. So maybe particularly strong instability of the flow on that day had made this impact particularly large, actually enter the window. But obviously the impact is totally different. And as for a global impact, this figure shows diagnostics on the quality of the forecasts produced by ICMWF since 1980 to 2014. And this is a correlation coefficient. The higher the correlation coefficient, the better the forecast. And you'll see that there was one significant increase in short-range forecast. This is moving average. At the time, around just around 1999, 140 bar was introduced. The one change, the most significant change in the quality of the short-range forecast was since 1987, was due to the introduction of 4D bar, 4-dimensional number assembly. And as far the compared quality of 4D bar, 4-dimensional variation assimilation, and ensemble kernel filter, it's difficult to make a really clean comparison. Same model, same data, same error, the same number model, everything equal except difficult. But a number of years ago, Buhner and colleagues made a systematic comparison and they got to the result that the two algorithms do not produce the same results because of non-linearity, but the present results who globally are of the same quality, of similar quality. Actually, I've come to the conclusion that the best method is the one for which you have taken most trouble. It's not a question of intrinsic quality, it's a question of how much you devote, how much energy you devote to optimizing them. Well, is some form of ensemble variational assimilation possible? The answer is yes, but I won't describe that. But you can perturb the observations, and for each set of perturb the data, and from each set of perturbed data, you do a variational assimilation. You obtain an ensemble of states, an ensemble of model orbits, which in the linear Gaussian case achieve exact Bayesian estimation. Okay, so now I'm sorry, but because of, I have to change files, so I think I do this. Diffusion d'écran, arrêté. So I go.
You have 5 minutes, Olivier.
Okay. I go to. Okay. Okay, I have now my second part. How do I have to restart the screen? Can you partager? Oh. Okay, can you see part 2? And can you hear me?
we can see. Yeah.
You can hear me. Okay, now so I'm going to speak about the question of stability and instability in the process. I alluded to that. But the question is, in this, there's now a link, deep link between assimilation and actually the theory of dynamical systems. Well, if there is uncertainty in the state of a system, and assuming for the time being that the dynamics of a system is perfectly known, uncertainty along the stable modes of a system will decrease over time, while uncertainty along unstable modes will increase. The stable modes being the perturbations to the basic state, to the real state, that decrease over time, and the unstable ones being the perturbation which increase over time. So a schematic way to represent that is that here, the full curve is the real state. At any point, there is a direction of unstable direction, the unstable manifold, and a manifold of stable direction, stable manifold. The uncertainty, if the uncertainty comes only from the observations, and the observations are homogeneously described in time, not concentrated in one particular mode at one particular time, but globally homogeneous over time. The uncertainty at the beginning of the assimilation period, or the observation period, will be concentrated in the stable manifold, and at the end, concentrated in the unstable manifold. And one can expect the uncertainty to be smaller at some middle time. Incidentally, this also shows that observation performed at the beginning of the observing period and observation performed at the end didn't bring the same information about the state of the system. if one is interested in reconstructing the state of a system over the observation period. And this is clearly visible, some experiments made by Carl Spirash on the simple system, a three-dimensional Lorentz system. It is a three-dimension. It has one unstable direction, one stable direction, and one neutral direction, which is the direction of the motion itself. And this is a projection about on the plane defined, the two-dimensional subspace defined by the unstable, stable, and unstable manifold. And assimilation, variational assimilation have been made of the system over a period over which the system is chaotic. The assimilation was done by repeated integrations, repeated assimilation of windows, which progressively became larger and larger. And as the length of the assimilation period increases, you see that the corresponding uncertainty concentrates at the end of the assimilation period into the unstable components and the unstable manifold. And of course, if you looked at the uncertainty at the beginning of the assimilation window, you would have the opposite, you would have concentration in the stable manifold. Since after an assimilation has been performed over a period of time, uncertainty is likely to be concentrated in nodes that have been unstable, it might be useful if you don't know exactly what the uncertainty is, at least in terms of cost efficiency, it might be useful to concentrate assimilation in nodes that have been recently stable, while uncertainty is likely to be largest. And this is what has been observed with experiments performed by Anat's revision. You have four panels. The panels on the top and the bottom on the bottom are actually the same ones. On the left, if you look at the full curves on the top panel, the curves correspond to assimilation periods of 1 day, 3 days, 5 days. This is the Lorentz 92 systems with 40 points, 96 system. And the full curves show the error in the assimilation average over a number of cases at the end of assimilation. And you see that it is largest at the beginning and the end of the assimilation window, and minimum somewhere in the middle. If one looks at the same time at the error along the stable modes, stable manifold, this decreases over time. One could say. Now on the right, these are results of experiments which have been devised in such a way that the assimilation is performed in a subspace of the full space. Subspace which has varying dimension, but it is obtained fundamentally by constantly evolving the same vectors and keeping a set of vectors, the same algorithm that is used for determining the Lyapunov exponent and the Lyapunov vectors. And this shows that when concentrating the assimilation in the unstable modes, the error is smaller than in the general case, and increases at the end of assimilation over the assimilation period, as it must be, because it is done along the unstable modes. And the error in the stable modes is negligible. So this shows that if you don't know well where the uncertainty lies in your background, in particular if you don't have a covariance metric or something which describes in detail the distribution of the error, concentrating the assimilation on those modes which are likely to have been unstable in the recent past is a good way to do it. And here you see the results, the error, residual error for different assimilation, length of assimilation window as a function of a number of vectors kept in the subspace in which you do the assimilation. And it is seen that the error is smaller when the number of vectors is just above the number of positive Lyapunov exponents, just a little above to take into account the possibility of fluctuation in the number of unstable modes at a given time. But during the assimilation in a subspace restricted to the dominant unstable modes, to the unstable modes, not dominant, to the unstable modes, is efficient. Of course, in a linear case with a full background covariance matrix, that would be obtained automatically because with the Kalman filter, because the background covariance error, covariance matrix will know that the error from the past is concentrated in the unstable modes. So it will be included in the matrix PV, but you may not have a total matrix, a complete matrix PV. Anyway, it's interesting to do. Many schemes have been developed. There are schemes which are called 4D EN-VAR, in which a variational assimilation, an ensemble variational assimilation is performed on a subset of vector determining one another. Often that substate has sufficiently small dimension so that it is not necessary to use an adjoint for computing the gradient and doing the minimization. For instance, the British Meteorology Office has a scheme of that type. I just write briefly a scheme which is shown, at least in theoretical situations, to be rather efficient. The iterative ensemble Kalman filter, defined by Bokeh and Sakov a few years ago. The minimization is performed at a control time T0 and assimilate observations over an interval TS-TL, TS not coinciding necessary with T0. And a subspace is defined, and if a subspace is small enough, the gradient of the objective function can be computed by finding different. Yes? Okay, I have 10 minutes. Okay. Okay, and an approximation Asian can be determined in the minimization algorithm. And once the minimization has been achieved, a new ensemble is obtained, can be obtained, and the whole scheme can be translated in time. So, for instance, as to carry for the next assimilation window, to carry the initial time TS at the time TL of a private assimilation, so that there will be no overlap in the assimilated observation, but that's not necessary. It's possible, but not necessary.
Olivier, I'm afraid if you want to have some questions, you will have to end pretty soon.
Okay. So already 50 minutes. Okay, all right. I thought I had some more time because I started it, but all right. Anyway, this shows that this scheme, because of the cycling of one step to the other, is more efficient than 4D VAR, which does no cycling, and then ensemble Kalman filter. Anyway, I also have two things: exact Bayesian estimation without any hypothesis for linearity or Bayesian or Gaussianity. Yes, there are particle filters which evolve particles in state space, each one with its own weight. But this is done in the simplest form, leads to collapse of the ensembles of particles, and the problem originates in the curse of dimensionality. The solution is resampling, that is removing particles with low likelihood. The likelihood of the particle is the probability that the observing, given that particle, is the probability that the observation is equal to what it is, and a number of resampling scheme which consists in removing particles with low likelihood and create new particles in origin in state space with high likelihood, including necessary, if possibly, future observation for evolving the particle because successive time. And this has been studied in particular by Peterian and Van Leeuwen, which have written a number of papers, in particular this one, in a French journal that is in English. And Peterian and his colleague Melanie H. have defined the equivalent weight particle filter, and in a case with state vector dimension 60,000, on the vorticity equation, the obtained results we show on the right, the truth, on the left, this is the result of the particle filter after something like 12 analysis, the analysis being separated by twice the time, decorrelation time between the fields, so that the original fields had been totally forgotten. And you see that there's a very strong similarity between the truth and the field reconstructed by the particle filter. So there are circumstances where it is possible to overcome the curse of dimensionality. Okay, now and just say that assimilation, which originated, sorry, can you say? Assimilation,
yeah,
which originated from the need of defining initial conditions for numerical weather forecast, has gradually extended to many diverse applications, first in climate and environmental sciences, and then in other domains. And this is a very limited list of domains in which assimilation has originated from the needs of meteorology or oceanography has gradually extended. Environmental science, magnetism, it has become a field of mathematical study itself. There has been a recent work performed with different assimilation algorithms and a cooperative work with different groups doing assimilation on the dynamics of the COVID-19 pandemic. It has progressively enlarged to many domains of application. Okay, well, thank you. I'll stop here.
Thank you very much, Olivier, for that interesting talk. There was a question in the Geopad and from Lars Nerger. He was saying that in ensemble data simulation, one expects the ensemble member to evolve naturally in the unstable directions.
Yes.
And then he was asking, so what is the advantage of the projection into the unstable subspace?
Well, the uncertainty, yes, the uncertainty in the unstable directions will increase as the ensemble evolves. But if I don't think, of course, according to what I said, knowing the uncertainty, the ensemble, by what it is, we know what the uncertainty is in the unstable directions. So maybe it can be useful to restrict the correction to the unstable direction. But as I said, in a linear Kalman filter, in which you evolve a complete covariance matrix for the error in the model, and you do an analysis at a given time, the background covariance matrix will know that the error is concentrated in the unstable modes. And so we'll take it into account in the correction. In the case of the particle filter, essentially the ensemble should know it also. And in the case of schemes like 4D and var, of course, it's a question of knowing if your description of the uncertainty at a given time, after you've done a 4D and var, and you have the ensemble at the end of the assimilation period, which you're going to use to the assimilation and the next assimilation period. Of course, it may be useful to identify in one or another the unstable direction and to restrict the correction to the unstable modes. I must say, I don't know if to which extent this has been done explicitly. It may be useful, of course, to take into account some knowledge of the unstable modes, but if information is large enough, it may not be the case. In any case, in the experiments which I showed, which were made by Anna Trevisan, it was shown that in the absence of the background error matrix, that was the case. But if some knowledge of the unstable direction is available, then it is beneficial to perform the assimilation in those reduced unstable directions. I don't know if it answers the question.
I think it was an interesting discussion. There are a couple more questions in the Geopad online. but we have to move on to Michael Gill. But if you can, I would appreciate, we would appreciate